liters of water will be changed by those 100 liters of acid base?
Well, you're adding lots of water, like 9,000 liters, or not 900, not 9,000, 999.9 liters of water. That's estimated to 1,000 liters. What changed is we can't use this equation. This is the hard part in chemistry. In math, the equation's always valid. You have a mathematical equation, it works, right? But in chemistry, some of these equations have certain restrictions on them. So for example, the Henderson-Hasselbalch equation doesn't always work because we assume that certain things must be true before we can use it. One of the things we assume that must be true is this. The initial concentration minus the change is about equal to the initial concentration. That works, if the initial concentration were fairly big, but if the initial concentration is extremely small, then it doesn't work so well. Yeah. And so in this case, we have to use, we have to figure it out. Actually, let me back up a step. Whenever we do the chapter 17 problem, we take the strongest acid plus the strongest base present. So the strongest acid present would be ammonium. It's stronger than water. And the strongest base present would be ammonia. But what forms when ammonium and ammonia react? Yeah, the same thing. So then what we do is we take the strongest acid and react it with the next strongest base. And so the strongest acid here would be ammonium. And the next strongest base would be water. Well, ammonium and water, that's just Ka. Or we take the strongest base and react it with the next strongest acid. And so we end up with these two equations. Ammonium and water is going to give us hydronium and ammonia. And then the strongest base, ammonia, will react with the next strongest acid. The next strongest acid will be water. And we're going to end up with ammonium and hydroxide. We look at these two equations. These two equations are familiar equations in chapter 16. This is Ka for ammonium. This is Kb for ammonia. And so what we have to do is we have to do these two, or do we have to do these two? We only have to do one. Why is that? Yeah, they describe the exact same equilibrium. Ammonia in terms of pH, ammonia and ammonium in terms of pOH. Now my preference is, since we're interested in the pH, I'm just going to pick the Ka equation because then I'll get the pH directly. So this will probably ignore that other equation for the Henderson-Hasselbalch. And so we'll get the same thing, but the only difference is we have to be careful because we might think Kw is going to be significant, but in reality it might not. And so what we'll do is we're going to choose this. As a matter of convenience, but not necessarily. But this one is stronger. And so really we should pick the stronger one. The Kb is actually greater than the Ka. So we should have picked this one, but we're picking this one with the realization that my thinking for the next step, do we need Kw or we don't need Kw, hinges on this. And so ammonium plus water is going to yield hydronium and ammonia. Ka for this, well, is going to be 10 to the minus pKa. I didn't calculate the Ka for this. And the pKa was what, 9.255? 2554 was that?
9.2553.
3. And so I'm going to go ahead and calculate that here. This is going to be negative 9.2553, which gives me a Ka of 5.5552 times 10 to the negative 10. It's pretty small. Whereas the Kb for ammonia is 1.8 times 10 to the minus 5. This one's going to be 5.6 times 10 to the minus 10. It's a huge difference. Okay, so I'm going to go ahead and plug in the concentration of ammonium. What was the concentration that we calculated?
For which, no, the,
1.28
Ammonium was 1.28.
times 10 to the negative 5.
And ammonia?
7.2 times 10 to the negative 6.
7.2 negative 6. Hydronium is going to be 0 initially. Then we're just going to let this equilibrate. So which way is this going to go? To the right. Yeah, it's got to go to the right. This is 0. So this is going to be minus x, going to be plus x molar, plus x molar. And so we're going to get 1.28 times 10 to the minus 5 minus x, which is going to be x. And this is going to be 7.20 times 10 to the minus 6 plus x. Now for the equation here, I'll just plug that in. So this is going to equal x, the hydronium times the ammonium, which is 7.20 times 10 to the minus 6 plus x, divided by 1.28 times 10 to the minus 5 minus x. So hydronium times ammonium divided by ammonium waters. Now, here's the critical part. For the Henderson-Hasselbalch equation to work, the equilibrium concentration must be the same as the initial concentration, because that's what we do. Henderson-Hasselbalch allows us to skip the ice table because we're making the assumption that the equilibrium concentration is exactly the same or close enough to the initial concentration. So this is the simplifying assumption that we make. We're going to go x times 7.20 times 10 to the minus 6, 1.28 times 10 to the minus 5. That. And so let's solve for x. That would be, clear it out of my calculator, I think. No, I didn't. Okay, so that is 1.28 times 10 to the minus 5 divided by 7.2 times 10 to the minus 6. That gives me an x value equal to 9.8759 times 10 to the minus 10. Oh, maybe it's okay. Maybe the simplifying assumption is still okay. Which one's going to be a bigger percent change?
7.2.
Yeah, and so let's go ahead and calculate the percent change based on that, which is going to be x over 7.2 times 10 to the minus 6. So I'll take this divided by 7.2 times 10 to the minus 6 times 100. Oh, I get a percent change of 0.01317. Is that what you guys got? So this is okay. Simplifying assumption is okay. It's actually pretty good. And so we'll go ahead and go with this one then. Now, The next question is this. If this were the hydronium concentration, which it is going to be 9.8759 times 10 minus 10. Would Kw be a significant contributor to hydronium? Okay. Yes, based on the concentration, but this solution is not an acidic solution. This solution is a basic solution. We should have used Kb, and the amount of hydroxide we're going to generate is like 10 to the minus 4. You know, if this is the amount of hydronium, the amount of hydroxide is 10 to the minus 4. If I had 10 to the minus 4 hydroxide, would you worry about Kw? No. And so this is the one trick to using, you know, it's a matter of convenience because I don't want to do a POH pH calculation, you know. But if I pick Kb, then we would never worry about Kw because we have so much hydroxide there. And so I should have picked Kb, but I picked Ka, and because I picked Ka, I have to keep in mind that this is not an acidic solution. In acid solutions, we're looking at all the hydronium contributors. In base solution, we're looking at all the hydroxide contributors. So I only did this to skip one step. That was it. This was a little shortcut. So I'm not going to worry about, because I know if I have this much hydronium, then my hydroxide is like 10 to the minus 4, or actually this is 10 to the minus, it's like 10 to the minus 3, you know, hydroxide. It's almost 10 times 10 minus 10. Do 1 times 10 minus 9, or no, be 1 times, 10 to minus 11. So anyway, this will be it, and then let's go ahead and take the pH of this. I'll take the pH would be the negative log of that. 9.8759 times 10 to the minus 10. So we got the same pH. What's going to happen is the capacity is going to be quite reduced. You know. Now, if we keep diluting it, you know, as we get to, let's say, 100,000 liters, you know, or to infinite dilution, the pH should approach that of 7 water. But here it's still okay. It just has barely any capacity. This is micromolar, 7.2 micromolar. Ammonia means you have to add like nanomolar, you know, to stress it. Because if you start adding too much, the pH is going to change quite a lot. So, I suppose we could do another calculation where we dilute it significantly, but we won't. If we keep diluting it, what's going to happen is we're going to get closer and closer to where the hydroxide is going to approach pH 7, where water is going to be more significant. We'll have to do Kw. Does that answer the question?
For part A, we did the solution dilution down to like from 0.1 liters to 1,000 liters. And even though we come with the same answer, I don't think we were supposed to, just based on the problem for part A.
For part A?
Yeah. I mean, it's really minor.
Oh, you mean the first part of this?
Yeah. I mean, we come up with the same answer whether or not we dilute it or not.
Yeah, well, that's the thing about buffers. Buffers are supposed to maintain the pH whether they're diluted or not. They'll maintain the same pH up to a certain point, and then it'll fail. So the dilution, it's just this 1,000 liters. If we were to dilute it to 1 liter, no big deal. We expect it. The ratio didn't change. Even at 1,000 liters, the ratio doesn't change. What we have to worry about is this. Just simplifying assumption. I mean, we could dilute it if you wanted to. We could dilute it a lot and then see pH change. You want to do that?
Like how much would you have to dilute it?
That's a good question. That just is based on experience. Thing is, what we could do is we could set up, a calculation where we can see where it starts to change, but it's hard to say without actually seeing some numbers. And so we could dilute this. Let's dilute this to 10 to the minus. Dilute this to 10 to the minus 50. That's maybe too extreme. 10 to the minus. No, let's see what's something simpler.
10 to the minus 10.
10 to the minus 10. 10 to the minus 11. Something like that. 10 to the minus 20. 10 to the minus 21. That would be pretty extreme dilution here. So we could just do a quick calculation. So 10 to the minus 21, 10 to the minus 20. Let's just try that. Okay, we'll go ahead with the simplifying assumptions since it doesn't take too much time, and then see what the simplifying assumption tells us. With the simplifying assumption, we have a problem though. 9.8759 times 10 to the minus 10. Could that be possible? It's impossible because the change is bigger than our initial amount. We're going to run out before we can get there. Even though we might do the, well, anyway, we could do the percent. What is the percent change? Percent change is like 10 to the minus 10, we'll just say, over 10 to the minus 21, which would be like a 10 to the positive 11% change. So it's huge, right? So it's going to be a fail. And so we'll have to do the quadratic. So go ahead and do the quadratic then. So the quadratic is going to be 5.5552 times 10 to the minus 10x. This will be negative 1.28. 1.28 times 10 minus 20 times 5.5552 times 10 minus 10 plus 7.1107 times 10 minus 30 is going to equal 7.20 times 10 minus 21x plus x squared. Okay, so let's get all the terms on one side. So I'll just get x squared. Okay, and then I'll add this to both sides. And so this is 10 to the minus 10. That's 10 to the minus 21. This is barely going to register on that. And so I'll just keep it at 5.5552 And then there'd be many, many more zeros, and then 721, so I'm not even going to carry that. 10 minus 10 x minus 7.1107 times 10 minus 30 is equal to 0. Okay, let's solve x here. So I get A is 1, B is 5.5552 times 10 to the minus 10. C is negative 7.11. There are 7 times 10 to the negative 3. .28 times 10 to the negative 20. .28 times 10 to the negative 20. Is that even possible? No, this is impossible because what's wrong here?
It was in the ammonia or ammonium is a strong acid.
The stronger acid. So, in other words, yeah, if we were to do this, then what would the, if this were the hydronium, the hydroxide must be like 10 to the positive 6, 1 million molar hydroxide. No, that's not. And the reason this failed is because now I cannot use Ka. I have to use Kb, and Kw is going to be a significant contributor to hydroxide. And so here's where it failed. And so I need to go and use Kb here. Because Kb is stronger, this is going to be a basic solution. So this would be like an advanced problem. 1.8 times 10 to the minus 5, quite a bit stronger. Ka is 10 to the minus 10. All right, so let's go ahead and plug in. Actually, let's just go straight to the equilibrium, save time here. What was the ammonia concentration again?
1.2.
Okay, the 10 to the negative 20, 21. 1.8 times 10, 28 times 10 to the negative 21.
Sorry.
20. Okay.
But yeah, that's for the ammonia.
Okay, 7.2. 7.20 times 10 to the negative 21. Okay, this is going to be minus x over. And then the ammonium was 1.28 times 10 to the minus 20 plus x. And then the hydroxide is just going to be x. And so I'm just going to skip some steps to save some time. 1.28 times 10 to the negative 20 plus x times x divided by 7.20 times 10 to the minus 21 minus x. Can you already see it's going to fail? I mean, the initial concentrations are so small, it's going to fail, the simplifying section. So I'm not even going to bother with the simplifying section. In this case, normally I do. And so we're going to get x squared plus, okay, this is going to be extremely small compared to this x. And so this is going to be quite a bit bigger. And so I'm just going to say this plus that is going to, we can ignore that. And so this is going to be 1.8 times 10 to the minus 5x. And then this is going to be minus 7.20. 7.2 times 10 to the negative 21 times 1.8 times 10 to the negative 5. So minus 1.296 times 10 to the negative 25 equal to 0. So let's go ahead and calculate x here. So A is 1, B B is 1.8 times 10 to the negative 5. C is negative 1.296 times 10 to the negative 25. Actually, we'll just do 7.20 times 10 to the negative 21. That's my x. Do you think water is going to be a significant contributor here? Yeah, sure. Water is going to be a significant contributor. And so let's go ahead and do. I should have left this here. Just running out of points. Let's see how much water is going to contribute here. KW is equal to 1.0 times 10 to the negative 14, which is going to equal x times 7.20 times 10 to the negative 21 plus x. I don't think the simplifying assumption is going to work. This initial concentration is too small. So we're going to go x squared plus 7.20 times 10 to the negative 21 x minus 1.0 times 10 to the negative 14. So let's go ahead and solve this. 7.2 times 10 to the negative 21. Negative 1 times 10 to the negative 14. Right on 1.00 times 10 to the negative 7, which means that this is going to be this plus x, which is going to give us 1.00 times 10 to the negative 7. Well, if that's the hydroxide, what is the hydronium? Okay, a couple of things to say about this. One, what is the pH now? pH is 7, so it's been way too dilute, right? And it's almost like pure water. In fact, it's like pure water. That's one. Two, this problem is actually a bit more complicated because this step is going to hugely perturb the previous step, which means this must be solved simultaneously. But even if we solve this simultaneously, it's going to come out about the same because if we continue diluting, it's going to be like pure water. And so if I solve this simultaneously, I don't expect that big of a difference, even though it's not totally right. And so it should have been solved simultaneously. Not going to bother. Yeah. Yeah, you don't have to memorize any of the Ka or Kb's. I just have a couple of them memorized, like ammonia and acetic acid. They're both the same number, not exactly the same, just the same to 2 sig figs, 1.8 times 10 minus 5. Ammonia and acetic acid are two of the most common. Okay. But other than that, I don't have any other ones memorized, except the strong acids, strong bases. All right, so yeah, we did it, but at what point does it go to 7, you know? Well, you know, you could do, probably the easiest thing to do is make a program to calculate it at increments, and you pick the increments that you want and then see where it changes, and then it depends on the system you're looking at. And so you do one as an example, and the thing to keep in the back of your mind is, you know, wait, am I getting too dilute? Maybe. And so it just should send out like a warning. Maybe the Henderson-Hasselbalch isn't going to work. You know, that's the kind of warning that we need. But these types of things come from experience. We experience because, if we have experience doing the calculation, then we can see.
This dilution is like billions of liters of water.
Yeah, right. I mean, if you took 100 milliliters and dumped it into a huge lake, is it going to make the lake's pH 9?
According to this math, yes.
According to Henderson Hasselbalch, yes, it would make the lake pH 9 because the ratio didn't change, right? But obviously, it's not going to make the lake pH 9. But, then you go, okay, well, lake, but what if I put it into a pool, swimming pool with a lot less volume? Do you think it's going to change the pH of the swimming pool, make the pH 9?
Tiny bit, but not that much.
No, then you go down to 5-gallon, jug. Is it going to make the pH 9 of a 5-gallon jug? Probably not. You get a lot closer, but this is the kind of thinking. We kind of know it, but we don't exactly know it. We could do a calculation, of course, and then figure it out exactly if we wanted to, or more accurately. Okay, were there any other questions? Okay, that's good. I'm glad you're doing the homework. I didn't do anything over the break. So you get your exams back this week. Although there's the rough draft. How's the rough draft coming along?
I couldn't find any articles. I emailed you about it trying to figure out how I can find articles.
Okay. Well, I was out. So articles for which one? For the did you search like Google Scholar? Are you guys familiar with Google Scholar?
Yes.
There's a little bit more scientific references on Google Scholar, so try Google Scholar.
Sorry.
I was gonna say, I like Google Scholar tends to like find all these really niche articles that just kind of don't really work for what I was working with.
Is this for the intro section? You guys are looking for some information for the intro section? The other thing is you could go to the library. The library, they have databases there, scientific databases. I think you can access it through the El Camino site too, and then just search.
Like Einstein? Yeah, I found some stuff that's like pretty, it's not super related to it, but I was like, I guess we're gonna talk about this random thing in my intro because I can't find anything else.
Yep.
That's kind of what I ended up doing.
All right, that's okay. We did the oxalato complex, which is at C2O4.
We found the article from the 40s.
From the 40s. You could talk about, the structure, maybe. Crystal structure. This is an article about the crystal structure of the potassium salt here. This one is 1952, it said. Yeah. 1952, active CRISP.
Yeah.
Probably this is, do we have the whole article here?
No, that's all.
The thing is, this gives you some other information. So what you do here is you look, are there any other publications by R.W. Burley? So the next thing I'd search is R.W. Burley, and then I'd search Jaeger. And then, these people, I'd search all these people who are involved in this and see if they wrote anything about this published. Obviously, they must have published something because they're talking about, or they could just be talking about crystals in general. It might not necessarily be related to this. What else do we have? There's some related ones. This is the ammonium rather than potassium salt. And so here we have the ammonium salt. But oftentimes, even though it's not the same thing, they might talk about the potassium salt down here, or there might be something kind of related to it. These are more structural papers here. This is active CRISP.
Yeah, so the potassium salt was mono, whereas the ammonium salt is tri.
Okay,
So it says something down
okay, yeah, so this is kind of what you do, see what you can find.
there. For the titration,
Mm-hmm.
are we doing the same format
Same format,
of lab? Okay,
right,
of report.
same format for the report. Here, let me ask you this. When you analyze the graphs, do you get exactly the same equivalence point for the pH curve, the first, what we call the first derivative, which is that hump, the slope, and then the second derivative? Did all those come out exactly the same equivalence point? They should have.
It's pretty close.
They're pretty close.
One maybe off.
0.1 off. That's pretty good. So these are the types of things we talk about in the discussion. When you analyze a curve, what did you do? Did you average the equivalence points for all four graphs or whatever? That kind of stuff, or did you, or maybe a lot of people's second derivative is worthless. They get a second derivative a lot that looks like something like this. And then where is it? Which one do you pick? Or it comes out way too noisy. You can't really see exactly that kind of stuff. So this is the type of stuff we talk about in the discussion section. When you analyze your data, what went into the thinking for analyzing the data, and then how did you come up with the numbers and this kind of stuff. That goes into the discussion section. What a lot of people do, let's say you had, what was your acid, ascorbic acid, or no?
Yeah.
Ascorbic acid. And a lot of people will write in the discussion section about ascorbic acid. So this you could just find on Wikipedia. Yeah. Ascorbic acid is vitamin C. Basically. All right. Any other questions? We're going to resume the homework session with chapter 17. I'm just going to quickly talk about this stuff and then we'll move on to chapter 18. But we'll do a lot of examples. There's certain things, when we're looking at a titration curve, the equivalence point. The equivalence point versus the end point. Have you heard those two terms? End point versus equivalence point? The equivalence point is when you have just the right ratio, stoichiometric ratio to neutralize it. But the end point, which is shown here, end point is when there's a change, a detectable change. Oftentimes you can't tell if there's any change, so we have an indicator. An indicator might not change at the exact point, the equivalent point, but it could be close enough. And so let's take a look at that right now. Here, with some examples. I'm going to go to indicators. All right, an indicator is just like a weak acid or a weak base. And the thing about the indicator is, like phenolphthalein, is it has a different color. So if I look at the acid form of phenolphthalein, which I'm just going to call H indicator, H-I-N, versus the base color, for phenolphthalein, the acid color is colorless, and the base color is pink. And so all indicators are going to have a different color. And this color is going to depend on the pH, because this is like a buffer system in a lot of ways. When we look at it, this is a weak acid and its conjugate base. The weak acid and its conjugate base, as long as we have both present, then the pH is going to depend on the pKa plus the log of the ratio of the base I minus to the acid Hi and In minus indicator, not iodide. So what happens is this. When we look at the base to acid ratio here, if we have a 1 to 10 or less, then what we see is the acid color dominates. If we have a 10 to 1 ratio or more, the base color dominates. But if we have something, what's that?
Let's say H3C plus.
H3.
In your equation.
H3O plus for Johnny. If we're in between these two, let's say between 1 to 10 and 10 to 1, let's say 1 to 1 ratio. If we have a 1 to 1 ratio or anything close, then we're going to get an intermediate color, that is mixed color. So for example, phenolphthalein. Phenolphthalein is colorless. So when we're at, let's say 1 to 10 parts, 1 part base, 10 parts of acid to 1 to 100, the acid is going to dominate or more. But once we get to, let's say, maybe a 2 to 10 ratio, we start to detect a light pink color. And the pink color comes from the base color here. The base color is like a darker pink. And so the mixed color here is going to be between colorless and pink. And then once we hit like a 10 to 1, then it's a solid pink all the way. We can go 100 to 1 or 1,000 to 1 or whatever. Solid pink. So this is going to be based on the pKa, where it changes color. And so right in the middle of this will be the pKa pH. That is, if we have a 1 to 1 ratio of base to acid, then log of 1 is 0, so pH is equal to pKa. So when we're at the pKa of this indicator, that's right in the middle of the 1 to 1 ratio. Over here, the pH is going to be the pKa minus 1. Okay, and up here, we're going to have the pKa plus 1. And so the pH range for the mixed color will be pKa plus or minus 1. And that's going to give us a mixed color here. So let's take a look at some indicators here. And then just... So for example, bromophenol blue. Bromophenol blue, the acid color is yellow, the base color is blue. The mixed color is green. Yellow and blue make green. And so it's based on the pKa. When we look at the pKa, it's 7.1. So at a pH of 7.1, we have a 50-50 mix of yellow and blue. At a pH of 6.1, then we have 1 to 10 mix of acid to base, and it's going to be a much lighter green. It's going to be right at the border there. And then at an 8.1, it's going to be a darker green or starting to go blue, perhaps, different shade. And so this is what I just wrote up here, this table. All right, so let's look at some indicators here. If we look at the first indicator is lyserine yellow. The lyserine yellow pKa must be around 11. And so between 10 and 12 will be the mixed color. And so from 10 down, it's going to be yellow. They didn't print it. I don't know why they didn't print it yellow all the way down. Probably the same ink. But it's just going to be yellow from 0 all the way to 10. And then once we hit 10, we'll have the intermediate, which is yellow, intermediate between yellow and violet. And then once we hit 12, it's just going to be solid violet all the way up past 14. If we look at the thymolphthalein, its pKa is around 10. The acid color is colorless, the base color is blue. So we're going to have an intermediate color between about 9 and 11. Phenolphthalein, if you look at phenolphthalein, it's colorless and red, they're calling it. And the pKa is around 9. And so it's going to start turning light pink at a pH of what? If the pKa of phenolphthalein is 9, it's going to start turning a light pink at what pH? 8. Yeah. So at about pH 8, we should start to detect a light pink color. And that's going to persist until we get to about pH 10, then it's going to go dark red. And you can't tell. And once it goes dark red, you can't tell what the pH is. You just know it's above 10. And when it's colorless, you just know it's below 8. Now, phenolphthalein, that tells us the endpoint. So the endpoint of our titration was at pH around 8, 8 or 9, say. We'll call it 8. Was that okay for our titration? We used phenolphthalein.
No.
Well, let's take a look at our titrations here.
Sounds like we should have used something a little bit less.
Yeah, actually, it depends on what the pH of the equivalence point is. I think one of the best indicators would be like bromethymol blue. Bromethymol blue has a pKa of about 7. And so if we neutralize the acid, then it should be green here, there. So bromethymol blue is perfect. It's perfect for strong acid, strong base titration. Because when we have strong acid, strong base, we make a neutral salt. The neutral salt should have a pH around here. Why don't we use bromethymol blue? We don't use bromethymol blue because it's much easier to detect the presence of the color rather than the shade of the color here. And so the bromethymol blue, even though it seems perfect for strong acid, strong base titration, isn't. But isn't so easy to detect. And so what we do is we'll take a look at some titrations and see what kind of error that leads to if our equivalence point and the endpoint aren't the same thing. And so let's take a look at first strong acid, strong base. Shoot this in PowerPoint. For strong acid, strong base, here, strong acid, we start off with a very low pH. It's strong acid. Strong acids will have a low pH. There are different calculations that we do in the curve. One is the initial pH, which is Ka. 2 is between the initial and the equivalence point. Between the initial and the equivalence point is just excess strong acid. Excess strong acid, the pH is going to be dominated by strong acid, so it's going to be low. The only difference is when we get close to the equivalence point. When we get to the equivalence point, we have so little excess strong acid that Kw becomes a factor. The pH goes to 7 here because of the extremely low concentration of acid. And so we might have to include Kw calculations very close to here. In fact, we have to include it here because that's pH. The pH is 7 at the equivalence point. So this would be like HCl and sodium hydroxide. HCl with sodium hydroxide makes sodium chloride. Sodium chloride is a neutral salt. Neutral salt is pH 7. And then we go excess strong base. When we go excess strong base, the pH climbs. Initially we have very little excess strong base. We're at 25, we go to 25.01, etc. The pH is going to go up, and then we just have strong base here. Now, the equivalence point, we should use bromethymol blue. Bromethymol blue is excellent because that should be green right there, but it's hard hard to tell because some people's green is other people's blue. And so here, we use phenolphthalein. But what kind of error is phenolphthalein going to introduce into our titration? And so when we look at it, yeah, the equivalence point is here, but the end point for phenolphthalein is here at pH about 8 or 9, and that's off. That's a huge error in terms of pH, but is that a huge error in terms of volume of titrant? Now, this is practically vertical, so the difference between here and here is maybe 0.01 or 0.001 milliliters. Not even a drop. Not even like a half a drop. And so the error is minimal. However, if we try to use alizarin yellow, alizarin yellow would hit it here. And so we would be off considerably because this is where it should stop, but we have to add more to reach here. And so alizarin yellow would lead to a big error here, but phenolphthalein doesn't. In the same context, methyl red here, it doesn't lead to much error. We stop the titration just a hair early, but it doesn't lead to a big error in terms of milliliters. And even bromophenol blue, bromophenol blue, we'd stop pH titration here, or the titration here, and still that's not much of an error. However, if we use thymol blue, then the color would change out here, which would be a significant error in milliliters. Okay. So that turns out not to be a big problem. However, what you had was not a strong acid. What you had was a weak acid. And so what kind of error would it have led to in a weak acid titration? So let's take a look at the weak acid titration curve. So we'll add here. In the book. So if we were to do this, like acetic acid and sodium hydroxide, one, acetic acid has a much higher pH. Two, at the equivalence point, we don't get a neutral salt. Now, the equivalence point here is not 7. The equivalence point is closer to 9. Why is that? The reason is because sodium acetate is a basic salt. It's got a Kb. And so in that case, here, then this is actually the perfect indicator for weak acid, strong base, because the salts are usually weakly basic, and so they're around here in terms of pH. And so phenolphthalein works out quite well. Bromophenol blue may lead to an error. It might be okay. So anything in this vertical range, but the vertical range is so short here. The reason the vertical range is so short is because we're starting off at a higher pH. And so we don't have as big of a jump up, and what that means is we're going to have fewer choices for indicators. Now, the types of calculations that we can do here are the initial pH, which is the Ka of acetic acid, and then this, the excess acid, but this is excess weak acid, and it's going to now be excess weak acid plus the product. The product of the titration's sodium acetate, which is the conjugate base. So this is weak acid plus its conjugate base. So this is called the buffer range here. And so the first step is strongest acid plus strongest base. Second step is buffer. That goes up to about here, around at the extreme here. We probably can't use the Henderson-Hasselbalch, but we pretty much use it over this entire range here, Henderson-Hasselbalch. That's step 2. And then at the equivalence point is just Kb for sodium acetate, so solution dilution is important there. And then up here is just excess strong base with weak base, the conjugate base. And so those are the calculations that are typical. Now for a diprotic acid, it's going to look like this here. The first equivalence point is going to be acidic. And the second equivalence point would be basic. So if you had a diprotic acid, phenolphthalein works pretty well. But for the first equivalence point, we'd have to use something else to catch that if we're using an indicator. Like methyl orange in this particular example. Okay, so let's see here. We'll look at titration calculations. Strong acid plus strong base. The initial is just Ka for the strong acid. And then between here and the equivalence point, would be step I, solution dilution. And then step 2 would be Ka for excess acid. That would be in this range here. Then here at the equivalence point, we have a neutral salt. pH is 7.00. And then up here, we would have, this is excess acid. Here we're going to have excess base, strong base. So step I would be solution dilution. And step 2 would be Kb. And Kb, in other words, is just hydroxide. Okay, for the next type of titration, we're going to have weak acid plus strong base. Okay, at the initial point here, what we have is just Ka for the weak acid. And then between the initial point and the equivalence point, we call this the buffer region. In the buffer region, we do step I, which is solution. Actually, we do step I, which is solution dilution. Let me write a little asterisk here. The asterisk is 4 millimoles. So let's go through millimoles as well. I do solution dilution. And then the next step would be strongest acid plus strongest base. And then the final step would be the HH equations. Here we're going to have a basic salt. The pH is going to be greater than 7. And so to do this calculation, first we do solution dilution. And then in the next step, we're going to do Kb for the basic salt. And then we have our excess strong base region. And the excess strong base, one will do solution dilution. And then 2, we'll just do, Kb, that is just the hydroxide. The weak bases we'll typically ignore. Ignore usually. The strong base is dominant, the POH, and then we'll convert it to pH. Okay, then we have the diprotic plus triprotic acid in strong base. So here we'll have our initial pH. So this will be Ka1, maybe Ka2. Probably not Ka3 if there is a Ka3. Actually, let's do diprotic here first. So this is buffer 1. So the first step is solution dilution. And the second step is strongest acid plus strongest base. And the third step would be HH equation. Although I'm going to label the steps a little bit differently. Yeah. Now the first salt we produce is what's called an amphoteric salt. So when we get to the amphoteric salts, let me talk a little bit about amphoteric salts here. An amphoteric salt would be something like HSO3 minus. HSO3 minus is there's going to be a Ka and a Kb. So for example, if I look at the Ka for HSO3 minus, it's going to be HSO3 minus plus H2O liquid. This is going to produce H3O plus SO3 2 minus. This is the Ka. And then I look at the Kb for this, HSO3 minus plus H2O liquid is going to produce H2SO3 plus hydroxide. Now remember when we're doing the buffers, we could either use Ka or Kb. We didn't have to do both, We could use one or the other. In this case, can we use one or the other? Just like for example, out of convenience, I'm just going to use Ka because I just want to go straight to pH. Doesn't matter if Kb is dominant, I'll just use Ka because I'd like to do that. But can I go ahead and do Ka and just completely ignore Kb? No, I can't. Why is that? The reason is they don't describe the same equilibrium. In the buffers, the Ka and the Kb describe the same thing. Here, when I look at the Ka for this, the Ka is the equilibrium between bisulfite and sulfite. When I look at the Kb, it's totally different. The Kb describes the equilibrium between bisulfite and sulfurous acid. And so these two are totally different. So what does that mean? Well, that means I could try it stepwise, but I'll tell you stepwise is going to fail. You know what this means? I have to do this simultaneous. So whenever I have an amphoteric salts require simultaneous equilibrium. because I have to have Ka and Kb, and they're going to be tied together by Kw. And so when I do this, it's Ka and Kb and Kw simultaneous. Now, it seems so simple, like, you know, a simple salt, like, for example, if I had just the salt, sodium bisulfite. Sodium bisulfite, wow, does that become complicated? You know, it doesn't seem so complicated, just sodium bisulfite, you know, figure out the pH, but it is complicated because you got Ka, Kb, and Kw simultaneous. Fortunately, somebody else has solved this for you simultaneously and come up with this very simple equation. Initially, this looks like a nightmare to solve, you know? But you do all this simultaneous stuff, and you make some assumptions, and you come up with a very simple equation. The pH for the amphoteric salt is equal to the pKa for the amphoteric salt plus the pKa for the conjugate acid of the amphoteric salt divided by 2. So actually the pH of this turns out not to be that difficult. It's just going to be the pKa for HSO3 minus plus the pKa for the conjugate acid of that, which would be H2SO3, divided by 2. And so where did this equation come from? This equation came from solving it simultaneously and then coming up with a simplified equation for that. Okay, sorry, I'm out of time here. I'll stop.